phoning Robert.
Hi.
Hello, Robert. How are you?
Good. How are you?
I'm doing so good. Let's see if... Oh. I don't know. Yep, just working out this keyboard thing. Sorry about that. So, Cryptography 101 with .NET Core. What do you got for us?
Lots of cool stuff. We're going to talk about hashing, symmetric encryption, asymmetric encryption, digital signatures, all sorts of cool stuff.
Great. Do you want to go ahead and share your screen? Oh, well, why don't you introduce yourself first? Sorry, what do you work on?
So I work full-time on an e-commerce website, and I'm also a Pluralsight author, and do a lot of conference speaking, and that'd be about it. ASP.NET developer.
So if we like Robert, there's plenty of content out there to go find.
There should be.
In cryptography. Cool, cool. Okay. So would you like to go ahead and share your screen and we can dive in?
Yes. Let me know when you can see it okay.
I'll let you know when we can see that. Let's see. We're having some interesting Skype delays.
I see that.
Let's see. There's a camera. He's melting. Yeah. I think he was attempting to share his desktop and Skype might have crashed a bit. Just a little bit. We're getting some very interesting melting graphics though. Everyone's saying to switch to Teams. Okay, we'll go ahead and restart Skype really quick and I'll just entertain and delay, which is my main job. Javier is here in the studio with me. We'll probably switch off. That's his hand. We'll probably switch off throughout our interviews and whatnot. Oh, looks like we have Robert back. But naturally, as soon as I switch to the screen share, it crashes again. Okay. Just switching back to me on camera, so we're gonna figure out this in a second. Oh, I think I see Robert again. Okay. Robert, can you share your screen? I think I saw it for a sec. Okay, that's me on Robert's screen, and now I can press the live share, and it's repeating it because all it sees is him sharing Skype. So maybe minimize Skype and then we'll be able to see. Hey, there we go. Okay, now we can see your screen, Robert.
Awesome.
Okay. Ooh, that was fun. People are excited that we took them through the matrix there for a second. That was
Sweet.
Cool. Okay, let's dive in.
All right. So like we said, we're going to talk about Cryptography 101 with .NET Core. The principles we'll talk about, cryptography, you can use any platforms. They're very familiar algorithms and things that you can take advantage of, but we're going to focus on the implementations in .NET Core. So a little bit about myself, I said, I'm a Microsoft MVP, part of the ASP Insiders, Pluralsight author, Progress developer expert, and Fiddler. And that's my Twitter handle. So let's get started. So some background, cryptography is the science of keeping messages secure. Why do you want cryptography? There's really 4 different things. Most people think about it for confidentiality. So you're trying to protect data from being read. So you just have something you don't want people to see. That's what most people think of when they think of cryptography. There's also integrity. And so integrity is where I want to verify that data has not been modified. So a lot of times you'll go to download sites, you'll see here's the download. They'll have an integrity with a hash to show you that you can trust that the data has not been verified. So we'll talk about that.
Robert, real quick, could you minimize the Skype at the top of your screen?
That guy right there.
We just like seeing all of your slides.
Is that better?
Yes.
Okay. So we've got authentication, where you want to identify and validate who a user is. And we're also going to have non-repudiation. So a sender can't deny later that he sent a given message. This is all in the system.security.cryptography namespace. That's where all these classes will come from. And most important thing, if you get nothing else out of this talk, don't try to write your own cryptography. I mean, this stuff is well vetted. A lot of people have seen it. A lot of people use it. It's built into the framework for us already. Take advantage of what's built in. Don't try to write your own. So first thing we'll look at is hashing. So the idea with a hash function is you have a one-way function, so it's easy to compute in one direction, but significantly harder to reverse. So a hash function is going to convert a variable length input into a fixed length. It creates what you could call a data fingerprint or a digest. And it's okay to see it. So if I have data that I don't care that somebody, I don't need to hide it from them, it's okay for them to see, but I don't want it to be tampered with. That's the integrity that we talked about earlier. That's where a hash function is useful. So as you see on the left-hand side, I've got some basic content, and I can run a hash on it, and it's going to create this data fingerprint or digest on the right-hand side. That's the hash. If I make even a single character change to the data that's on the left-hand side, I'll get a vastly different hash. So the idea is I can use it, run a hash against the data, see that the hashes match, so I can see that things haven't been tampered with. So let's take a look at a demo for hash functions. Don't know what's happening there. Okay, so the pattern will be very familiar here for all the cryptography that we use in .NET, so I'll spend a little bit of time on this one. But I start with some initial plain text. So I've just got a string here that stores, in this case, this is a simple demonstration of hashing. I'm going to use the SHA-512 class to do the hashes. That's part of the SHA-2 family. The SHA-1, MD5s, all of those are not considered safe anymore. So you should use a SHA-2 functions. I'm going to use SHA-512. And what I'm going to do on this line, you'll see, is very familiar with all the other cryptography we'll do. I have my string, and I need to convert it into a byte array so I can use the cryptographic functions. They just all operate on byte arrays. So the first thing I'm going to do is I'm going to call the get bytes. So I pass get bytes, the plain text string. There's lots of different ways I could choose to encode this. UTF-8 is a pretty common encoding scheme to take strings. So I'm going to convert that, do the UTF-8 encoding, and then I'm going to simply call the compute hash function. And as you can see from the comments, I'm going to get back a byte array here that's got 512 bits. That's just because I use SHA-512. Now I want to display that on the screen. So I'm actually going to use the bit converter class. There's lots of different ways to do this. I'll show you later how we can use base 64 encoding. There's times where I want to be able to use the hash on a query string and such. So I want to use characters that aren't going to conflict with other things on my URL. So in this case, I just call the bit converter. I say I want it to go to string. And as you can see up above here, it's going to give me back something that looks like this. So I'm just going to strip out all the dashes. So I just end up with a basic display. So let's look at what that looks like. So you can see here, here's my initial string, and then what it hashes to here. So in the example, if I go back, you can see even if I were to go change this, if I uncommented that and had a much larger string, the actual hash will be a fixed size. It's just based on what the hash is. So that's basic hashing. If we have some time later, we'll talk about where you might want to use some of these techniques. Like I said, it's common if you go to download from a given site, they often list their hash. So they'll say, here's a SHA-256, etc. That way you know after you download it, you could run the same algorithm. It's going to do a hash, even though it's a huge file. It'll be a really small hash, and you'll be able to compare and say, that's what the site said they had. That's what I had after I downloaded it. So I know that nobody's tampered with that. So that's a good use of hashing. Now we'll get into what most people expect for cryptography, and that's encryption and decryption. There's going to be two different kinds. So we'll talk about symmetric algorithms first. And they're symmetric because the encryption and the decryption are going to use the same secret key. So we're going to have a secret to share between the two partners that want to exchange data, and we need to keep that key secret. So if we follow along in the diagram, on the left-hand side, I've got the plain text. That's what I want to encrypt. I'm going to run my encryption algorithm with a secret key. The result is the ciphertext. That's just the encrypted stuff I want to send. The person receiving the data will do the decryption, and they're going to use the exact same secret key. That's why it's called symmetric. And if they do that, they're going to get back to the original plain text. So the primary attack against this, as far as if people are going to try to break this, they either are going to try to determine what the secret key is, and if they couldn't intercept that or otherwise determine what it is, they're going to try a brute force key search. They're just going to try all the different possible keys. So the main problem with this, it's really fast. It's used a lot, but the key distribution is difficult. So we'll talk later about situations where I need to share with somebody on the internet that I haven't otherwise come in contact with. It's hard to give them the secret key because how would you give it to them ahead of time in a secure manner? So there'll be places for symmetric, like we said. There's a couple main classes built into .NET. And we're going to focus on the primary one that most people use today is AES encryption. So US government, a lot of others, this is just the common symmetric algorithm that everybody's using. In .NET, the symmetric algorithms are called block ciphers. So they're going to take my string and break it up into individual blocks and encrypt each block one at a time. That's why it's called a block cipher. There's a couple different modes that you can use, ECB or CBC. I won't get into all the details of these, but basically, if we use CBC, which we recommend that you use, when you encrypt the first block of the data, it wants to add more randomization into the symmetric algorithm. So it wants to take some random data from the first block you encrypt. It's going to use the result of that as input into the next block that it encrypts. So essentially there's some extra randomness done each time it's encrypting blocks of your original data. So the question for that then becomes, how do they get random data for the very first block that you're going to use? That uses what's called an initialization vector. So the idea with that, again, is just some random data that's going to be used to seed the first block for your encryption. It doesn't need to be a secret. So you'll see when we look at the diagram that I'm going to transmit that along with, and I'm never going to reuse it. It's always going to be unique for each set of data. That's all that's important. So let's take a look at a demo of symmetric algorithms. So I've got a web page. We'll look at the page first. So I can come out here and type in some random plain text. I can hit encrypt. We'll see that it created the ciphertext, but it also gave me the initialization vector. So that's what was used to seed the first block of this encryption. So I need to send both of these two things. I'm going to send the ciphertext and this initialization vector. Again, now that the ciphertext is encrypted, it's safe for me to just send both of these pieces. Again, the IV, it's fine if that's visible to people. If I hit decrypt, we'll see that I get back the original plain text like you'd expect. So let's look at how this is implemented. So when I do a post, I happen to be using Razor Pages. And so again, you can use this console wherever you want. I'm going to give sample code at the end that has a lot of examples of practical ways to use cryptography in an ASP.NET website. So that's why I chose to host it in here. But the first thing I'm going to do is I'm going to actually create an AES cipher. So we'll go up and look at what that looks like. It's pretty straightforward. I just use that class and say create. And I listed on the right-hand side what some of those defaults will be. I'm going to set the padding mode. So for the padding mode, it's fine to use the default. I like to use this padding mode because what it does is you take your original string, you're going to break it into blocks. That very last block isn't going to magically be the right size, 128 bits. So the algorithm needs to pad out the rest of that block. By using this ISO padding mode, it's going to put random data in the rest of that block, which again, it just helps with cryptography to be able to use more random data when you're doing things. So I like to use that for the padding mode. I left this in here if you want to test later. If you do a padding mode of 0 and you use the wrong mode, every time you encrypt the same piece of data, it will always end up with the same encrypted ciphertext. By using these other defaults, even if I encrypt the word yes 20 times, every time it's going to turn out having something different because of the mode that we're using with CBC uses that initialization vector to get the original random text to use. I'm doing this only for a demo. I'm setting the key. So obviously it's not a good decision to store my key directly in the code. We're not going to have a lot of time today to talk about ways to store keys securely, but for the demo code to be able to give it to you, I wanted you to be able to see you can just generate some random bits, and that's what I did to create that key. So now what I have, I've got the actual AES cipher. As we saw before, when I did the cipher, it created some initialization data. It created that first block of random data to use for encryption. I wanted to be able to show that on the page, and so I did a conversion to base 64 it so that when I displayed it back in the web page, you would actually see it in a visible form because it started as a byte array. To do the actual encryption, I create an encryptor. I again do the UTF-8 encoding that I did before. That takes my plain text string and converts it into a byte array. And then I call this transform final block, which does the actual encryption. And then I chose in this case again to use base 64 encoding so that I could display it on the screen as a string. Decryption is similar. I create the same cipher. I do kind of the reverse. And then here I'm doing the create decryptor. So again, the main point is just you look very quickly. This is a well-established algorithm that lots of people use that's highly secure, and it really doesn't take much .NET code at all to be able to take advantage of it correctly to do my encryption. So that is symmetric. Talk about asymmetric. So the idea with asymmetric is the two partners are going to create their own public-private key pair, and they're not the same. That's why they call it asymmetric. So in this case, if I want to send to someone else, I'm going to get their public key. I'll take the plain text. I'm going to use the encryption using their public key. Once I do that, I've got ciphertext. And the advantage of asymmetric is because I use their public key, the only thing that can decrypt this now is their private key. So obviously the receiver is going to hold on to their private key, make sure nobody learns that, but they're free to give out their public key wherever they want. You'll see it on people's blogs. You'll see it in email signatures. Anybody then can take that public key, do encryption, knowing that only the person who has the private key can do the decryption and get back to where they started. Problem with asymmetric, so it's great because it's easy to distribute keys, especially with people that you haven't even worked with before. So for instance, you came to my blog, you'd be able to get my public key. We wouldn't need to talk in advance for you to be able to send me things that are encrypted. The bad news is it's about 1,000 times slower than symmetric algorithms. So you'll often see in practice, like HTTPS and TLS, they actually use asymmetric to encrypt a session symmetric key. So in other words, they generate a random symmetric key. They will exchange that symmetric key using asymmetric encryption so that they can safely do that, and then they continue. Again, some of the very popular classes we'll talk and focus on the RSA class. So we'll do a quick demo on that. So very similar to what we saw before. I'm going to create, I'll show you the page quick. I can type in some text, do an encryption, and then I'll do the decrypt, get back to where I started. So very similar, I'm going to create a cipher like I did before. In this case, I just use RSA. I have created a set of public-private keys that I have stored in this variable. So now what I can do is take the plain text. I'll do my UTF-8 again to do the encoding to get it into a byte array. I'll call the encryption method, which uses RSA and the public key from that keychain. And then I will base 64 it so I can show it on the screen. And And a similar thing for decryption. So again, you'll see it's very simple to do this. I've got examples in the code for how you can create RSA keys. So later on, you can see how to create keys for both asymmetric and symmetric by using some of these other classes and pages. But basically, that's how easy it is to do encryption when you're using .NET Core. So we'll talk quickly about digital signatures. And this provides both integrity and non-repudiation. The idea is I'm going to hash the contents of a message, and then I'm going to sign that hash with my private key. By default, it doesn't provide confidentiality, but I'm going to show you in the diagram how you can do that as well. So if we follow along here, I've got some plain text. I'm going to encrypt it using asymmetric just like I did before. I'll use the receiver's public key to do encryption. I'll get ciphertext. I'll use hashing to compute a hash. Once I have the hash, I'll sign it with my private key, and that will become my signature. So now when I send the ciphertext, the person will be able to use the receiver's private key to decrypt it. They'll be able to use my public key to prove that I'm the person who signed it. So again, they have non-repudiation, we've got integrity, and we have confidentiality, all in one big approach here as far as using this in .NET Core. A couple cool things that are coming with .NET Core 3.0. We now will have authenticated encryption for the first time. So we talked about AES encryption before, and we've talked about hashing. This combines the two of them so that I can do the encryption, send it to you, and not only will you know that you can decrypt it, but you'll also be able to use the hash to verify that it hasn't been tampered with. So there's two new classes that come in .NET Core 3.0. Like I said, this is the first time we've had access to authenticated encryption, so that's cool. They've also got an expanded list of cryptographic key formats that we can import and export compared to what we had in the past. So in summary, don't write your own encryption. Use trusted algorithms and implementations. Use hashing when you want to validate integrity of data or to prove that you both know the same secret. And then generally with encryption, you want to use symmetric algorithms because they perform so much better unless you have special needs for asymmetric things such as digital signatures, you need to do key exchanges, etc. And again, know your threats, choose the proper countermeasure. So you need to know what you're trying to do, whether it's confidentiality or non-repudiation will help guide what the right type of algorithm and approach will be when you're doing .NET Core. Some quick resources. I have a Pluralsight course that's an introduction to cryptography in .NET, so it goes through the same contents in a lot more detail with a lot of practical examples using .NET Framework in that case. Here's 4 very good books that talk about cryptography. So if you're interested in how AES actually functions or how RSA works and all the math and the technical background, you can look at those. If you want a good background just on the history of different uses of cryptography, what people did, how it got broken, both of these books are excellent books for that. And that's my Twitter. That's an email address where you can reach me. That's where I have the slides and the code available. And we can either do some questions or I can show a couple examples if we have a little time.
Okay, thank you so much. So can you hear me all right, actually? Oh, sorry, can you hear me all right, Robert? Okay, we'll see if this works. We need to switch off our mics because there is an echo that we haven't solved yet because half of the team needs to sleep at some point. That's the fun of doing 24-hour live streams. So I will forward you the questions, Robert, and then I will, let's see, Skype Q&A. There we go, okay. And then I will be able to unmute you and then I'll mute myself so we avoid the echo. Okay. So here we go. So in general, people really appreciate the advice about not writing your own hash functions. Do you have any more to say on that topic?
No, I think, like I said, it's nice that we have open source, trusted, well deployed, well tested hashing and cryptography, the encryption, asymmetric, all of that stuff built into the framework. A lot of people have said that they can write their own cryptography, and they think that by writing their own algorithm and keeping it secret that they'll be able to do a better job and be able to encrypt stuff. And virtually every time that's been tried, that's a lot of times when people go on an audit and look at specific issues with breaches and such, they find that people do things like that. Take advantage of the stuff that's built into the framework. Just don't try to write your own. If you really want to be a cryptographer, go to a place where you have other cryptographers work together on things like .NET Core and have other people that can help review it, because it's complicated stuff to create. Hopefully we've seen that it's easy to use.
Yes, that would be the power of teamwork. I like it a lot. It's always good to have other people checking your work. Okay, so normally when one is using encryption or decryption, it's ideal not to store the encrypted ciphertext on the database, but just the encrypted hash. No?
A good example would be if you don't, so for example on passwords, you traditionally would store hashes. You don't need to reverse that data to get their original password. You'll take the new password they type, you'll hash it, you'll compare it to a hash. That works in that situation. When you're storing data that you need to be able to get back and retrieve and actually see the value of, you're going to have to actually use encryption, in which case you'll want to use decryption as well. I've got some examples in the sample code you can look at. A good example of a public website that needs to take data, you could put a public-private key, put the public key only on your web server, so if anybody got it, who cares? Encrypt stuff on the front end using the public key, store it encrypted in the back end, and then the only system that needs to decrypt it and use it has the private key. But it's fine. I mean, if you need to get the data back, you need to be able to decrypt it, so you have to use encryption. It's fine to store that in the database. Passwords are an example of I don't really need to back it up and see it. I just need to make sure it's the same, and that's why they use hashes for that.
Great. Okay. Sorry, I have to now type 4 buttons while we transfer. When was just a general question, what is the best place to store the encryption key?
I only caught the very end of that, sorry.
I know. Okay, I'm trying to ask again, but I have to switch all of the buttons. Okay, what is the best place to store the encryption key?
That's a very long answer, depending on what you have access to, what kind of system you have. I tend to like the example I just went through. If I've got a public-facing web server, I generally treat that web server like it's compromisable. At any time I could have a zero-day exploit, things like that. So I really don't want to have a key stored on that machine. That's where I think storing the public key makes a lot of sense. So if I use asymmetric, put a public key on there, I can even put that in my code if I want. It doesn't matter, because if anybody sees that, it doesn't help them. Only on my internal behind the firewall system would I actually have the private key that could do that decryption. There's Azure Key Vault. There's other techniques depending on what your deployment environment is, how paranoid you are, what your threat models are, how people attack you, etc. But in general, I like doing the public key if it's a website.
All right. Well, thank you so much for joining us, Robert. That was very interesting. Next up, we have John. What is John going to be talking about, Javier?
John is going to be talking about Xamarin and modern Android applications. So we're going to hang up here on Robert, and we're going to call him right up. So stick tuned. And Kendra and I are going to switch, because we got to take breaks from time to time.
Water or something?
And we'll go from there. All right. Thanks so much. Thanks so much, Robert. All right.